Alright, so in this video we're going to take a look at the control model of the permanent magnet synchronous machine. So the overall machine model as well as how to control it. And I've gone ahead and drawn it already. And of course you should probably take some time, pause this video, take a look at the equations and see how this model is made. I decided against drawing it all out in the video, otherwise it would extend this video and make it really long. But essentially, what we're doing is the equations here. So we have, let's say, equation 1, we have equation 2, and we have equation 3, right? So we're using these equations to understand how we can put these blocks together. So for instance, equation 1 relates VSD to ISD, right? So you have ISD is your output here, and VSD is your input here. But you have some intercoupling of these two channels, and by channels, I mean like I call like this bottom part of the channel, and I call this part of the channel path, whatever you want to call it, really. So this 1 over SLD RS is determined based on this part of the equation here. And at the bottom, the 1 over SLQ plus RS is determined based on this part of the equation here. And so you know what the input to that is. The input to that should be the right side of the equation. And then the input to the first so that the input to this should be the right side of equation 1, and the input to this should be the right side of equation 2. And you can construct those using whatever techniques you would like, but I've drawn it a certain way here. Again, there's more than one way to draw this, of course, but what we're trying to look at is how can we construct something that's insightful, right? So once you generate ISQ and ISD, as you do, let's say, at this point, then what you have to do is you have to combine them in order to generate the torque, because we want to create a model that input or that takes your voltage VSD and VSQ as the input, as well as the machine speed, and produces a torque, right? So the output here is the torque. The input to this model is omega m, VSQ, and VSD, right? And so again, take some time, pause the video here if you'd like. Really look at how this thing is developed. It's a good sort of exercise to be able to develop a model like this on your own. But like I said, I decided to skip over it in this video because if I sat here and drew the entire thing out, this video would probably drag on longer than it needs to. So we have some additional things that we can draw actually, and that are useful in such a system. And those things include the following. So we have some other little block diagrams. These are smaller, so I didn't draw them beforehand. But let's say you have a speed here, omega m, coming in. It's the same speed that you had at the top. And what you're going to do is you're going to integrate this. Maybe we can change the color of the integral sign just to be consistent with that. Or we can even call it a 1 over s. Let's call it a 1 over s, because we know 1 over s is integration. And so the output of this is going to be theta m. So the integral of the angular speed is the angle itself. And then if we take that theta m and we multiply it by p over 2, then we get the angle theta r, which is the rotor flux angle. Well, it's the electrical angle, and it is the same. In this case, the rotor flux angle is the same as theta r. It's not necessarily the same in the induction machine. So in this case, we can measure it directly using a shaft encoder, right? So we can say all of this is from shaft encoder, right? And then let's say you want to also get omega r, because omega m is the mechanical speed and omega r is like kind of like you think of the electrical speed, because we know that there is a difference between the two in the general case, and in this case as well. And the difference between the two is dependent on the number of pole pairs, p. And so we say you multiply that by p over 2, and you get the output of this is omega r. Now, why is this useful? Well, omega r might be useful for some calculations at some point, but these angles are actually important for the DQ frame, ABC to DQ frame conversion that we do, sort of, and sometimes you hear that called the Park transform or the inverse Park transform, depending on which way you're going. We'll just call it ABC to DQ. Q. And so you'll have an output, you'll have two vectors or two quantities coming out. You'll have three quantities going in. The quantities going in are Vsa, Vsb, and Vsc. And the quantities coming out are obviously Vsd and Vsq. Now you have another thing coming in here, because remember, your angle or your frame rotates with a certain angle. And that angle is theta r. And this is the same theta r you would get from your shaft encoder. Now, we'll also need at some point, well, we may or may not, but I guess we do in this case, we will need a dq to ABC, and this would be for the currents, and or, well, I guess if we need one for the voltage as well. So I'll draw one for each, and then you can kind of pick and choose whichever ones you need accordingly. But this is ISD, and this is ISQ, this is ISA, ISB, and ISC. And again, you need this same angle, theta r, to be there. Okay, and like I mentioned, in permanent magnet synchronous machines, the rotor flux angle is the same as theta r, and is therefore measurable by a shaft encoder, unlike the induction machine where there's no direct correlation between the rotor flux vector position and theta r. So you need what we call a flux observer, which we've seen in the past already. So how do we formulate control loops for all of this now? So we have these equations. Why don't we just copy these equations up here as opposed to rewriting them? So we'll save ourselves some time rather than rewrite everything. So we have these equations here, and from these equations we can we can determine what our control loops should look like. So we have this part and we have this part. And what I'm going to do is I'm going to call this part here UD, and I'm going to call this part here UQ. Okay? And based on this, we can formulate what the plant should look like. So remember, the left side of the equation is the plant, which is the 1 over s plus whatever it is. Well, I guess we can, in the general case, it's 1 over tau s plus 1. And you can have specific cases where it's equal to a bunch of different things. So why don't we then first take equation 1 and turn that into a control loop. So from equation 1, we know that we have some input to some block, and we have some output, right? So what is the input? Maybe I can draw that a little bit longer so it gives me a bit more space. The block here for equation 1 is 1 over SLD plus RS. The input to that block we called UD, and the output of that block we obviously know is ISD, right? So this is going to be ISD. And UD is going to come from a control function, some type of compensator or controller, depending on the textbook you use. They might be referred to in different ways. And so we can call this some compensator KD of S. And here you'll have your comparison between the feedback and the reference. And so your signal gets fed back there. Negative feedback, so there's a minus sign there. We can call this difference ED, and we can call this signal here ISD star. So that's the reference you're giving to the control loop or to the machine, whatever you want to call it. And that comparison obviously results in some error, and then you get some signal UD that you should have. You feed that to your plant, and then you can go about it that way. Now, part 2, or equation 2, I guess, you can do the exact same thing, but in this case you'll start with ISQ, right? So I guess at this point we've cat's out of the bag. We already know what's happening here, so we can say ISQ will go into some comparison, basically a sum block or difference block, depending on which way you like to look at it. This is KQS. We'll call it Q because it's the Q frame or the Q component. And here, in this case, we have 1 over SLQ plus RS. The output of this is obviously ISQ. And here you have a minus sign, and this is EQ, and this is ISQ, this is UQ. So this is what your general control loops should look like. Now, KQ and KDS can both be PI compensators because the values ISD and ISQ are DC. This was the entire purpose of doing the the ABC to DQ frame transformation, because now we can basically track AC quantities, three-phase AC quantities, I should say, using PI compensators. If you actually want to track an AC quantity or an AC reference, you end up having to design much more complicated control functions, and so we save ourselves the trouble by applying these transformations. So again, KD and KQ can both be PI compensators. So then you can generate your VSD and VSD and VSQ references based on UD and UQ, and so on, based on what ISQ is, based on these relationships up here. Right? Right. So, what's next? Next, what we can do is we can look at the overall implementation of how these control loops would be implemented, I guess, in terms of feed forwards, cancellation, a bit more intricate, because this is a very general current control model, right? So I've lumped everything together with UD and UQ, whereas we actually want VSD and VSQ to be separate from those, right? So let's create a little bit more detailed of a model, and to do that, we're going to start with signals coming in so this will be a little bit more complicated than the other one, but we'll have something like this, I guess. And we'll say that this out here is going to be VSD star, right? And this is going to be ISD star, right? So you have an ISD star that will generate some VSD star based on some relationships. So here you'll have a minus, and this will be ISD, right? So the actual ISD that you have. And this here will be KDS. So this ISD again comes from the machine, right? It's a feedback. And this signal also goes around here into, well, maybe we make that a little bit bigger, into this block. We call this LD. And LD will be multiplied by something. And that something will be actually omega m, so maybe we can include that now here as well. So that's omega m, and omega m gets multiplied by p over 2 to convert it into omega r, right? And the output of this will go into this block here, so it'll be multiplied by that signal, and then it'll go down here, and will also get multiplied by another signal. And the other signal that it's multiplied by is going to come from another block here. And this we can say is LQ. And I'll explain in a second where these blocks come from, because our other control loop, the generic thing that we did, didn't have any of this. So it begs the question, where did all this stuff come from? So we can draw here then the next sort of comparison, I guess, between the reference and the, would like to scroll down a bit, between the reference and the actual measured value. So you can subtract this, and this again is ISQ reference, and this is ISQ actual, or measured, however you want to refer to that. And so the actual, maybe we don't go over there, that looks a little awkward. So we go around like this. So the actual also gets multiplied up there. And this, after taking this difference, you can you can pass it through your compensator, and this compensator is KQS, and then the output of this compensator goes to some block, or some adding, subtraction, something like that, and then the output of this is VSQ star, right? Now, these terms in the middle, we call them feed forwards. And the reason we call them feed forwards is because what they do is they decouple the signals from one another. So if you remember in the vehicle model that we showed at the top of, or earlier on in this video, I should say, there were these crisscrossing type of signals, right? So now those crisscrossing type of signals end up causing issues because what they do is they sort of result in coupled behavior. So one control signal depends on the other. Now, that's obviously not ideal, and not that it's not ideal, it's actually very bad. So we try to decouple, and in order to decouple stuff, we have to use what we call feed forwards. And I'd have to move this a bit here, so maybe we can put this like this and call this like this, maybe call this omega m, call this p over 2, so that I can take, well, I guess I can just go across here. I don't have to go all the way around. So let's go down here. So maybe that was all for nothing. Anyhow, but yes, the purpose of the feed forwards is to decouple the behavior of the two loops such that one loop changing does not affect the other changing. So that's lambda m. So now I'll show you what I mean. So we have here, so you say that, okay, the output of this compensator is VSD plus some quantity right here. If this quantity didn't exist, let's suppose we get rid of this feed forwards. The output of this compensator is VSD. But now what we do is we've added ISQ times LQ times omega R, and we've added that to VSD. But if we go up here, we see that this has this LQ omega R ISQ, right? So if this has LQ omega R ISQ plus VSD, then what we need to do is we need to make sure that we negate the effect. So you'll see this here as well, right? So you see this is VSQ, this is ISQ times LQ times, well, the output here, which I haven't labeled, the output here is omega R, right? So you essentially have ISQ times LQ times omega R being added to VSD. So now how do we eliminate that in our control signal? We just do the opposite, right? So the opposite in this case means that this should be negative, right? So you want to subtract the effect of that thing. That's how you decouple this. Now, in the case of Vsq, you'll notice that these two quantities are negative, right? So if these are negative, then what you can do is, and sorry, this should be a positive inside here. So maybe I think we did that at the top as well. We did. So let's fix these as well. So this should be positive. Both should be negative, negative. So in order to eliminate the effect of whatever's in the parentheses here, what we do is we add this quantity to the second or to the bottom path, right? So basically you have ISD here being multiplied by LD here, being multiplied by omega R here, and then being subtracted here. So you want to add this term and you want to add this term here. So that's exactly why we go down here and we leave these as additions. So then we have Vsq and Vsd references, right? So typically, according to the schemes that we've discussed, this is typically 0, and this is from torque reference. So of course the ISQ current component is related to the torque reference, and so you can have a torque reference coming from some machine or vehicle characteristic, let's say, and the reference can be multiplied by a factor, divided by a factor, the lambda m's and all that kind of stuff, 3p over 4, and you can get ISQ reference from TM. Okay, so the last thing I would like to do here is to give a brief description of how this whole overall system would work. So in practice, so in practice, suppose you'll have some inverter, we'll call it INV. Now the output of this converter will be a three-phase, some type of three-phase system. And let's draw it like this. And this will be fed into some machine, let's say. The output of the machine goes to the vehicle. And on this side of the inverter, you'll have, let's say, some battery going into some, let's call this a boost converter. This would be some type of boost converter. Between here and here, you would have a DC link capacitor, and we can say the voltage of this capacitor is VDC. And here, to actually control the inverter, you would have to use some type of pulse width modulation, PWM we call it. That doesn't really look like an M, so let's fix that. PWM, and the input to PWM is usually some type of carrier signal. Let's say it's a triangular carrier or a sawtooth, sometimes they make it. And the references to the PWM will have to come from a VSD and Vsq references, right? So the ones we just generated. So VSD reference, let's say VSD reference, Vsq reference. This is DQ to ABC. So that means these three signals are VSA, VSB, and VSC references. So VSA reference, VSB reference, VSC reference, right? And so you'll send some gating pulses to your inverter. Now, on the output side, I guess if you call it that, you have some type of feedback happening, right? So you'll have here ABC to DQ, and the output of this, I guess we drew them backwards. So we actually needed DQ to ABC for the voltages and ABC to DQ for the currents, but at the top we drew them in the opposite. It's not a big deal. I mean, you can apply this transformation to any three-phase signal. So here you have ISD and you have ISQ, and we're going to do a little simplification here, I guess. So you have one current here, you have one current here, and if you think I forgot a third thing, I didn't. So you have ISA plus ISB plus ISC equals 0, right? That means ISC is equal to minus ISA plus ISB, right? So you can measure only two of the currents and determine the third one with the other two components, which is convenient. So we're going to take, let's take some summation block here. So subtract that, and then take this and subtract that as well. So both of these get subtracted and then sent to ISD or to determine ISD and ISQ. Now, how do we determine the theta? Because we need theta, right? So you would have some type of, like we said earlier, shaft encoder or some type of device that can measure the speed of the rotation. You can take that speed, you can pass it through an integrator if you'd like, or you can, some things you can measure the angle directly. Let's say you can't. Let's say you can only measure the speed. So you take omega m, right? So you take omega m, so that's omega m. The output of this thing is then theta m. So this is now theta m. And now, but we need theta r, right? So if we want theta r, what we do is we take this and we multiply u by p over 2, right? So now we have theta r. So we can send a theta r to here, and we can send the same theta r to there. And so this is now theta r, right? So this is an overall system sort of in a practical setting, explaining how I guess I should say how this is implemented in practice, because what you have is you have a bunch of different things going on here, but we have to understand how all this ties together. So the thing that we're responsible for really in all the discussion that we're doing, I guess you can highlight and would say that it's basically this part, right? So this is what we're taking care of. And the inverter and the boost converter, we're kind of saying that, okay, just imagine these things come from these. We're idealizing them and saying that they're approximately equal to 1 and they're perfectly ideal, which is a fair approximation to make. For most part, they are pretty close to ideal if designed properly. So let's do a recap. What did we do? We had these equations that we developed. Well, we looked at last time. We didn't really develop them. We kind of just explained them. We have these equations for the permanent magnet synchronous machine. Based on these equations, you can develop this machine model. This model, again, is useful for control, is useful for simulation, for analysis, for understanding how the machine operates. And then we have these extension, I guess, auxiliary type of things. And these will help us. So this is how you can get your angle theta r and theta m based on omega m. You can apply dq to ABC or ABC to dq. And again, like I said at the bottom, I kind of flipped these, but I mean it makes no difference if you change if you change this to VSD, VSQ, and change this to ISA, ISB, ISC. It doesn't really matter. In any case, you can take these equations, you can simplify them a bit, and then you can get these generic conceptual control loops. So this is like in theory, the control loop looks something like this. But if you actually want to implement it, it should look something more like this, because this considers the fact that your ISQ comes from a reference, ISD should be 0, that we're actually generating VSD and Vsq references and not just some UD and UQ, although UD and UQ are the effect of the feed forwards and such is taken into account with these blocks here. And then we looked at this sort of generic system, of a practical system, I should say, and perhaps we can label these as being ISA, ISB, and ISC. And so given all that, you can determine all the things that you need to properly operate your electric vehicle using a permanent magnet synchronous machine. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.